I think we can start. Probably we'll be finishing within half an hour or so, but I want to have more dialogue with you in terms of answering questions and discussions and things like that. So far, what we saw was basically we looked at a single droplet. So basically, you had a you had a substrate, you had a precursor film, and then we looked at one droplet. And we were looking at the stability of this droplet. And we looked at stability from two angles. One is a quasi-steady stability analysis, and the other one was a transient growth analysis. And we proved that for a multiple, for a binary mixture where both A and B are evaporating, for both A and B are evaporating, it is probably best to have a transient growth analysis, which is more amenable to the system. Now, the thing is, what we're going to do is basically, whenever we have any kind of a system, whether it's a reboiler, whether it's a condenser, whether it is anything, you just don't have one droplet, you've got multiple droplets. Okay? And these multiple droplets can be either, they're normally never arranged in a very geometrical pattern, they're basically random. Okay? So what we are going to look at now is if you have multiple droplets, especially when you have multi-component droplets, and in this case when we say multi-component, I'm going to show you two methods again. Second method would be tomorrow, but what we're going to do is we're going to add another droplet. Okay, we are going to have another droplet which is something like this. So one of the things you may ask is, what is the distance between the two droplets? Okay, when the precursor film is not, when the precursor film stops interacting between the two and so on. So that's an important question. So basically we are looking at this system here. So we've got A and B. This is work done by Debreci actually. So this is mixture A and B. Both of these, there are two droplets here, and it's a 2D system. Okay, so we begin with a 2D analysis, and again, because the extent of the height with respect to the length is small, we can use a lubrication approximation here as well. So basically, you've got two droplets. They are separated by a distance. Okay, they're separated by a distance, and you've got evaporation from both ends. Okay, and basically, if you closely look at the contact line, you would see that there is also a precursor condition. Okay, there's a precursor film, and again, we also again we say that there are linear properties. That we are looking at. Okay, so the kind of droplets we are looking at, I'm going to show you the materials as well, but typically they should be agreeable to this kind of linear properties. Okay. The other important thing is in our previous system, when we looked at just one droplet, we ignored what is happening in the gas phase. We just said that, okay, it's going to evaporate and it's just going to go. But the moment you have another droplet, you cannot make that assumption. Okay, the moment you have another droplet, you will have a combined effect of vapor affecting the evaporation dynamics of the whole system. And that's very, very important. So you need to have a combined system. So you need to actually evaluate what is happening in the vapor phase. So while we do lubrication approximation here, we are also considering the vapor phase in this case. So this is a step up from what we have done before. So previously when we looked at films, we were just looking at the film and the dynamics of the film. We almost ignored what is happening in the vapor phase. This is a one-sided model. This is some sort of a 1.5-sided model. So what we are looking at it is, we are looking at the lubrication level approximation, but at the same time, we are looking at what is happening in the vapor phase in a very, very rudimentary style. Not a complete convection system, but we are looking at using a Laplacian equation. Okay, so we will have what is happening in the vapor phase simply by a Laplacian there. So you've got a concentration equation in the vapor phase, and that is going to be linked very closely to what is happening at the interface. Okay, so obviously the way it is linked is through Fick's law. Okay, so basically you can say that if your vapor concentration is this, then evaporative flux can simply be given as Fick's law from the interface. Okay, so basically this is a very simple way of tackling the vapor phase concentration equation. The other important thing is, you talk about evaporative flux, What is evaporative flux? Evaporative flux is given by the Hertz-Knudsen equations. Again, this is a molecular kinetic theory. So again, so we'll be using the Hertz-Knudsen equation. You've got a constant here. Basically, it's basically the difference between the local pressure and the vapor pressure, and that will give you the evaporative flux. And if you split everything, you will get this whole thing in this way. Okay. So basically, again, the difference between what we have done before and what we have done here is that we are including the effect of the vapor phase. Okay? We are including the effect of vapor phase, but we are not including it completely. We call it as the so-called 1.5-sided model. Okay? So when you have a two-sided model, you're accounting for the convection in the vapor phase, you're correcting for everything in total. Okay? That's what we do in DNS. But this is again a 1.5-sided. We are looking at vapor phase, but in a partial sense. Okay? Just by the Laplace equation in the vapor phase. Okay, so again we'll have similar scaling relations. Again we'll have similar epsilon there, which is where the height of the droplet is much smaller than the width of the droplet and so on. So we'll get very similar set of equations, nothing really changing much there. You will have this is basically the way your h as a function of t and space. So this is how you will get. You will also get x, which is basically the concentration as a function of time. Okay, so you'll get everything, and this is what is happening in the vapor phase. Okay, so basically what we have done is we've used our the previous lubrication equations. We have substituted all these things, and we'll evaluate the height of the interface as well as the concentration at the interface in this way. Okay, so this is concentration at the interface with respect to JA. So you got the evaporation flux of A, and you also have evaporation flux of B in this way. Okay, and this is obviously there more than one droplet, so you'll have to consider the vapor phase effect as well. Okay, so now the first thing Debrishie did is we looked at pure ethyl acetate droplets, and the reason we have looked at pure ethyl acetate droplets was because it was easier to do experiments with it. Okay, now if you have a single droplet and if you have a multiple droplet, there is a difference. In case of a multiple droplet, you have a region close to the droplets where there is vapor accumulation, and that will suppress evaporation at a later stage. Okay, and it is called as vapor shielding. Okay, this is basically vapor shielding effect here going on in between the droplets. So what we're going to do is we're going to look at how these things evolve. So you start off from these two droplets, and what they do is as they evaporate, because they are pure droplets, the only capillary force that is there is the thermal Marangoni. So because of thermal Marangoni, they actually come together, and as they evaporate, they form a single droplet. Okay, they'll form a single droplet, and then the whole thing evaporates. So, but obviously they are evaporating as they come together, and this is for a pure ethyl acetate drop. Okay, now if you look at it very carefully, the first graph I would ask you to concentrate is on this one. Okay, so if you look at a single droplet, you will have a very fast evaporation time. So you can see that you almost evaporated by 1300 or something, T equal to 1300 or something. But the moment you have two droplets, it's gone back. Okay, it's a very slow evaporation rate, and that's because you've got vapor accumulation. So in fact, if you zoom this image, there are actually two droplets, and this is the region very close to the droplet, which is red in color. This is where the concentration field is extremely high, and which is actually preventing more further evaporation. Okay, so whenever you have a population of droplets, you will have the effect of vapor. You will have the effect of vapor in terms of vapor shielding. They can suppress evaporation. If you look at this particular figure, so this is basically the rate of mass as it drops because of evaporation. If you look at this particular figure, we are plotting mass flux with respect to the distance as it evolves. So if you look at early times, so if you look at the blue phase, so at the contact lines, you will have this kind of a peak. At the contact lines, you will have a peak at maximum evaporation. Okay, so obviously these two guys are seeing each other. They are at a suppressed evaporation, and this is again seeing the atmosphere. So basically, this has more evaporation there. So, and this is how basically it will evaluate. I mean, so as obviously these droplets are moving together, so you can see that blue is slightly far apart, the black is closer, green is further closer, and finally they merge. Okay, so basically you will have you will have you will have this kind of asymmetric evaporations from both ends of the droplets. But again, one of the main things one of the main takeaways here is that your evaporation is much more faster than the diffusion time scale. That's why you've got vapor accumulation here. The vapor is not just going off immediately. Okay, you've got vapor accumulation here because diffusion time scale is much larger. Okay, so it takes time for it to diffuse, but again evaporation is faster, so you'll have vapor accumulation, and therefore you increase the evaporation time of the droplets, especially when you have more than one. Now what we're going to do is we're going to look at different droplets. We're going to look at water morpholine, and water morpholine has got a very peculiar property. So in case of water ethanol, water is less volatile than ethanol. In case of water morpholine, water is more volatile than morpholine. And the reason why Debryschi took this system is because it was easier to do experiments. With water ethanol, things happen so fast that it's very difficult to see. So this is a much slower system. And typically this has somewhat, the properties are something like this. So you can see that the relative humidity is approximately 30%. You can also see that the ratio of the molar ratios between the two is nearly the same. You've got a certain thermal conductivity ratio, you've got a certain surface tension ratio. Surface tension ratio plays a huge role as well. I'm going to come to that, and then you'll have difference in latent heats. Okay, so if you look at this, what we will define here is whenever the effect of temperature we are looking at, we'll consider it as a Marangoni number. So if you say that the Marangoni number has increased, so increase in Marangoni number means that the surface temperature has been increased. Okay. Delta T is T minus T vol, or T vol minus T ambient, something like that. So if Marangoni, if Debryschi presents like Marangoni he has increased Marangoni, he is essentially increasing the temperature of the substrate. Okay. One thing you can see is that when Marangoni number is about 0.01, that means that T is closer to T vol. The T ambient and T vol are closer to each other. That is when Marangoni number is significantly small, you have this attraction behavior. Okay, you've got this attraction behavior, and we wanted to check why is that so. Okay, why is there an attraction behavior at this? But then if you increase your Marangoni number by tenfold, that means that you're increasing your substrate temperature. You actually will have some sort of an attraction, and then you have repulsion. Okay, some sort of an attraction and you have repulsion. And whenever he says delta X, this is the original positioning of the droplets. Okay, so you can go as close as you want, but we don't want to go as close as immediately they'll merge. Okay, so you need to be careful. So I think we decided that the maximum distance, minimum initial distance we can go to is delta X about 3.5 or something, because otherwise in experiments it was very difficult to control. Okay. Okay, so we looked at that, and then again as you look at the contact points, you can see that it has a very similar evaporation fluxes as we saw in the pure droplets, but there is a bit of a difference. I'm going to come to that. There's a bit of a difference. You can see that it's quite asymmetric. It depends upon, so obviously these two contact lines are closer to each other, so they have very similar evaporation fluxes there. Okay, now we'll look at it very carefully. We'll look at what happens with these things. So one of the things we wanted to look at was, obviously you've got two contact angles, you've got two droplets, so you've got four contact angles. So we look at the contact angles which are seeing each other, so which are actually looking at each other. So this is theta R1 and theta L2, and we'll find that theta R1 and theta L2 behave in the same way. So these two guys will behave similar, and they're completely different from these two. Okay, so these two guys are almost lying on top of each other, and L1 and R2, they lie on top of each other because they are farther away from the system and they're exposed to the environment. Okay, so this is how your contact angle actually changes as evaporation goes through. Okay, as evaporation goes through. So basically, he calls it capillary flow because he's purely looking at how your theta has changed. Okay, but then what we want to check was why are they attracting each other? So basically, after several experiments, we noticed that if you keep increasing your thermal Marangoni, you actually accelerate the repulsion of droplets. So basically, thermal Marangoni is the one which is actually pulling the pulling the droplets apart. So whenever you have, so if you remember, we had seen a video where you had these different droplets placed on a slide, and you can see these droplets moving, and some of them are going away from each other. That is possibly because their local thermal Marangoni constants are driving them away. Okay, are driving them away completely. Okay, what brings them together? What brings them together is the solutal Marangoni. And the solutal Marangoni is not very simple. That's the effect of the vapor phase around this. So when you say thermal Marangoni, it's basically the substrate which is taking a role. But when you look at solutal Marangoni, it's a combination of concentration at the interface, but it's effectively what is happening at the vapor region. Okay, so whenever you have a solutal Marangoni effect, when it is more stronger, you have basically attraction. So if you increase the temperature of a substrate, you will ultimately drive these things far away from each other. But then if you want to defeat that, you increase your solutal Marangoni and they're going to come together. Okay, so you can actually manage coalescence or basically segregation of droplets based on basically this. Okay, so one of the things what he has done is basically looked at again. This is a Marangoni scale, so essentially you're changing the surface temperature with respect to concentration. Okay, this is the concentration of the more volatile component, and what he has done is he has done several experiments at I think York University, Toronto, with Alidad. And looked at what is the behavior of these droplets. And if I remember them correctly, all of these are water morpholine, if I remember them correctly. So you can see that in cases where you've got these blue regions where you have more of attraction, you can see actually droplets coming together and coalescing. But then there are other regions where you can have both attraction and repulsion. So in this case, again, this is a water morpholine system as far as I remember. You can see that initially they were far apart, and now they're slowly coming together and so on. Okay, so one quick takeaway is basically that all of these droplets, when you have multiple droplets, you've got a far complex kinetics, far complex physics that is going on. If you have if you increase the substrate temperature, if you increase your thermal Marangoni, you actually will drive them apart. But if you increase your solutal Marangoni, you actually bring them together. So I think hopefully we'll have a publication soon. We are about to submit one. So and I can then share more of it. I think I'm nearly done with this aspect of the work. So any questions? Yes. Yes.
So if we will take the single component mixture, then what will the attraction or repulsion?
So when you have a single component, it is completely thermal. It's completely thermal. So based on the thing is, again, if I'm assuming that the environment is clear and it's not polluted, if you have, we have also done experiments where we pollute it with ethanol vapor, and then you can actually bring the, because you have solutal Marangoni coming up then. Okay, but then if you don't have a solutal Marangoni, they generally tend to be going away from each other.
Initial evaporation curve.
Yeah.
So one side you are having the bigger volume,
Mm.
and in other side you are keeping the volume concentration like 2 droplets of half of volume.
Oh yes. Basically, we start from the same point. We have started from the same point. Yeah.
So will there be any point if separation is extremely large?
You get to this. So if the separation is extremely large, if the droplets are not able to see each other vapor-wise, they behave like single droplets. Yeah.
And another point is, whenever So maybe there will be some time lag for the vapor to accumulate
Yes.
between the two droplets and
Yes.
silt. So can there not be a bit faster evaporation rate initially, and then there should be
Transition towards that. So basically, so we found that in systems which evaporate quickly and then they suddenly slow down. So you do see that in systems. But here, because he was testing water morpholine, it was a much slower system anyway. So it was a much more regulated system. But for water ethanol, you actually see that. If you bring them closer to each other, initially there's fast evaporation, but then everything suppresses. So yeah.
And is this spreading and evaporation simultaneously taking place? So is it like maybe controlled into inertia of droplet or heat transfer, or is it?
Yeah, good question. So basically, at least on the modeling side, because it's a lubrication theory, we've killed most of the inertial terms. But then when we do numerics, we find that inertia does play a role. Does play a role, especially if you, in the region of contact angle of 40 degrees to 60 degrees, inertia plays a huge role. So inertia does play a role. Yeah.
I'm sorry, I missed the initial part. So currently, did you consider this reverse diffusion from vapor to droplet as well?
We have reverse, the thing is, yes, so we have not put any sign to the diffusion. So it can, in effect, you can actually have condensation as well, completely dependent upon the local vapor pressure. So in a sense, yes, we do have that, but in most of these cases, your vapor pressure of the system is high enough to make sure that it is going away. Okay, but in principle, yes, you can have condensation as well. In fact, if you remember, I had shown one video wherein you had absorption. You got these two droplets, one droplet shrinking and the other droplet growing. That's because of absorption of water. So in those cases, so we can see similar things. So we have done some work already where we have 100 droplets, and then you got some of these droplets actually growing in size because there's condensation happening on that.
And in experiments, when the two droplets are of same size, so rate of evaporation is almost same for both, or can there be some asymmetry?
There is usually some asymmetry. So typically, one of the biggest problems in experiments is how to deposit these droplets at the same time. So people do syringes, they have these syringe systems where they can put them, but they do two at a time. But the most easiest way is having a very low volatility system and just keep dropping them and let them pass. Yeah. Yeah.
And so all these are in the ambient air of the experiments.
Yes, ambient, completely ambient. I think the relative humidity was 30% or something.
And these simulation results, are these some two-dimensional simulations, or?
These are 2D. These are 2D, but tomorrow we'll see 3D. Tomorrow we'll see 3D. We did 2D simulations before because it was easier to get some initial results, and then we wanted to see zones where 3D is essential. So we're just focusing 3D on those zones. Yeah.
And these are heavily pinned contact lines.
Yes. So the simulations I'll show tomorrow, they are pinned, but these guys, if you look at the experiments, they move. So here, because there's a precursor film, there is no restriction. And in fact, you will see that you will also see the way contact angle changes with time here. You can see how the contact angle changes with time. He also has velocity plot. What is the contact line velocities? Yeah, I'm not shown it here, but yeah. So you will see that these are moving contact lines. Yeah. Yeah.
So probably there is difference of temperature in the inner side and the outer.
Yes, yes. There's always a difference. Yes.
How strong is it?
So basically, the way it happens is the outer edge is always cooler than than this edge because there is evaporative cooling that is going on. But here, because evaporation is suppressed, it is slightly warmer. But then, yeah, the thing is, in effect, the contact line, the way I can say is, if you have a contact line system like this, okay, so you've got these guys. So obviously, by default, we assume this is temperature of the wall. So we can expect that this is at a temperature of the wall here. We expect that this should be at the temperature of the wall because they're so close to the wall. But what would happen is, because of evaporative cooling, this would be slightly lower than TW. This would be slightly lower than TW, and this would be slightly higher because there's vapor shielding.
So though in contact angle it is visible that there is some curvature difference, can that curvature difference will not, that is already.
Yeah, I mean, if you want to see circulation, yes, it imposes a circulation here. So you've got a circulation current there. So we can see that. I mean, I'm going to, tomorrow when I'm showing the full 3D, you can see the circulation patterns. Yes?
It's a kind of ballpark. So what we can see, the two droplets are actually approaching.
Yeah.
So what is happening? Probably some kind of viscous dissipation is happening at the surface.
Yes.
So that is one force, and there is one force which is trying to actually attract or repel. So what is the order of magnitude that?
Oh, order of magnitude. So here, so typically viscous dissipation is, because the size of the droplet is really small, we can expect the viscous dissipation to be quite negligible. But it's a, given the main driving force here is basically solutul Marangoni, so that has a stronger. I think it's about 5 or 6 orders of magnitude stronger than the other things. Hydrophobic cases. Yes. No, so here this is a different case. So here, the model, these cases are only for contact angles less than 30 degrees. Okay, so contact angles are less than 30 degrees. But if you have a hydrophobic case, what will happen is there are a few things which will be different. One of the key things that will be different is, I'm going to show these equations here. Hold on, okay, yeah. So I think it would be probably the previous set of equations. I'll just show here. Yeah. So if you have contact angle, if you have lubrication theory, what you will get is you will have just the momentum in the x direction. You will have the continuity and all that. Okay. Now, if you are going beyond, if you are going beyond, if you are going towards a hydrophobic case, what will happen is you will not only have the x momentum, you will also have the y momentum equations, because epsilon is not small. Epsilon is actually big. So when epsilon is actually big, all of the terms become very important. You can't neglect it's no longer h. So epsilon is, it could be probably greater than 1. Okay, so that means you will have x momentum equation, you will also have y momentum equation. So you'll have more effect of inertia which is happening in the droplet, and that can cause currents inside the droplet. Okay, so I would say that if you want to go for hydrophobic systems, then yeah, we can't use lubrication modeling at all. Any further questions?
How much time does it take for the two droplets to actually merge?
I think he mentions it there. So if I start the if I start the experiment again, I think it took about, I think it takes about 10, 11 seconds. I mean that, so yeah, it's quite fast, but this is comparatively slower than water ethanol. Yeah. Yeah. But I can ask Debrashi exactly how much time it takes.
The effect in patterning, etc., has not been considered,
No,
right? That's
that will have its own complexity.
This means here, like all the results are only for the two droplets. If the droplets are more and more,
Yeah, I'm going to show you tomorrow. Yes. So if you have more number of droplets, you can actually use lubrication theory. If you have a linear line of droplets, you can use it, no problem. But if you have more in the three-dimensional, in the span-wise direction, then you have very different effects. In fact, you will see that if you have an array of droplets tomorrow, so if you have an array of droplets, sorry, let me see, let me go back again. So if you have an array of droplets, so if you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this droplet is surrounded by this is the center of the droplet. So this will have the slowest evaporation rate. But the pattern over here, this is more symmetric. But all of the droplets will have a completely different dynamic motion inside them. Okay, they'll have a completely different motion inside them. So you'll see that tomorrow. Good. Yes.
So if we use this with different droplets that have a heavier vapor, let's say, I'm expecting that the rate at which they are coming close would be reduced.
Yeah, you can change the dynamics completely.
So
So
we can stop the merging
yes,
altogether.
you can stop them merging together because this side is not evaporating at all because you don't have any. The vapor has shielded it so well that you're not evaporating one side at all. So so what will happen is all of the convection currents goes towards the side of the droplet. So evaporation is more pronounced from this side. So tomorrow what we look at is we look at DNS of evaporating droplets, but I'm also going to look at boiler surfaces. So you've got DNS of boiling because evaporation and boiling are, yeah, of the same phase change, but they have completely different thermodynamics. And obviously we look at, in real systems, you don't have one droplet or two droplets, you've got many droplets. So we look at boiling surfaces, we look at evaporating surfaces, which are used in all kinds of chemical as well as nuclear industry. So we'll see all of that. Yeah. Anyway, I'm here, so just ask me questions.